Stanford University.
Okay, so welcome to CS231N Lecture 3. Today we're going to talk about loss functions and optimization. But as usual, before we get to the main content of the lecture, there's a couple administrative things to talk about. So the first thing is that assignment 1 has been released. You can find the link up on the website. And since we were a little bit late in getting this assignment out to you guys, we've decided to change the due date to Thursday, April 20th at 11:59 p.m. This will give you a full 2 weeks from the assignment release date to go and actually finish and work on it. So we'll update the syllabus for this new due date in a little bit later today. And as a reminder, when you complete the assignment, you should go turn in the final zip file on Canvas so we can grade it and get you grades back as quickly as possible. So the next thing is always check out Piazza for interesting administrative stuff. So this week, I wanted to highlight that we have several example project ideas as a pinned post on Piazza. So we went out and solicited example of project ideas from various people in the Stanford community or affiliated to Stanford. And they came up with some interesting suggestions for projects that they might want students in the class to work on. So check out this pinned post on Piazza. And if you want to work on any of these projects, then feel free to contact the project mentors directly about these things. Additionally, we've posted office hours on the course website. This is a Google Calendar. This is something that people have been asking about, and now it's up there. The final administrative note is about Google Cloud. As a reminder, because we're supported by Google Cloud in this class, we're able to give each of you an additional $100 credit for Google Cloud to work on your assignments and projects. And the exact details of how to redeem that credit will go out later today, most likely on Piazza. So if I guess if there's no questions about administrative stuff, then we'll move on to course content. OK, cool. So recall from last time, in Lecture 2, we were really talking about the challenges of recognition and trying to hone in on this idea of a data-driven approach. We talked about this idea of image classification, talked about why it's hard. There's this semantic gap between the giant grid of numbers that the computer sees and the actual image that you see. We talked about various challenges regarding this around illumination, deformation, et cetera, and why this is actually a really, really hard problem, even though it's super easy for people to do with their human eyes and human visual system. Then also recall last time we talked about the k-nearest neighbor classifier as kind of a simple introduction to this whole data-driven mindset. We talked about the CFAR10 data set, where you can see an example of these images on the upper left here, where CFAR10 gives you these 10 different categories, airplane, automobile, whatnot. And we talked about how the k-nearest neighbor classifier can be used to learn decision boundaries to separate these data points into classes based on the training data. This also led us to a discussion of the idea of cross-validation and setting hyperparameters by dividing your data into train, validation, and test sets. Then also recall last time we talked about linear classification as the first sort of building block as we move toward neural networks. Recall that the linear classifier is an example of a parametric classifier where all of our knowledge about the training data gets summarized into this parameter matrix W that is set during the process of training. And this linear classifier, recall, is super simple, where we're going to take the image and stretch it out into a long vector. So here the image is X, and then we take that image, which might be 32 by 32 by 3 pixels, stretch it out into a long column vector of 32 times 32 times 3 entries, where the 3, again, where the 32 and 32 are the height and width, and the 3 give you the 3 color channels, red, green, blue. Then there exists some parameter matrix, W, which will take this long column vector representing the image pixels and convert this and give you 10 numbers, giving scores for each of the 10 classes in the case of CFAR10, where we kind of had this interpretation where larger values of those scores, so a larger value for the cat class means the classifier thinks that the cat is more likely for that image, and lower values for maybe the dog or car class indicate lower probabilities of those classes being present in the image. Also, so I think this point was a little bit unclear last time, that linear classification has this interpretation as learning templates per class, where if you look at the diagram on the lower left, you think that so for every pixel in the image, and for every one of our 10 classes, there exists some entry in this matrix W telling us how much does that pixel influence that class. So that means that each of these rows in the matrix W ends up corresponding to a template for the class. And if we take those rows and unravel, so each of those rows, again, corresponds to a weighting between the values of between the pixel values of the image and that class. So if we take that row and unravel it back into an image, then we can visualize the learned template for each of these classes. We also had this interpretation of linear classification as learning linear decision boundaries between pixels in some high-dimensional space, where the dimensions of the space correspond to the values of the pixel intensity values of the image. So this is kind of where we left off last time. And so where we kind of ended up last time is we've got this idea of a linear classifier, and we didn't talk about how to actually choose the W, how to actually use the training data to determine which value of W should be best. So kind of where we stopped off at is that for some setting of W, we can use this W to come up with 10 with our class scores for any image. So, and some of these class scores might be better or worse. So here in this simple example, we've shown maybe just a training data set of 3 images, along with the 10 class scores predicted for some value of W for those images. And you can see that some of these scores are better or worse than others. So for example, in the image on the left, if you look up, it's actually a cat because you're a human and you can tell these things. But if we look at the assigned probabilities, well, not probabilities, but scores, then the classifier, maybe for this setting of W, gave the cat class a score of 2.9 for this image, whereas the frog class gave 3.78. So maybe the classifier is doing not so good on this image. That's bad. We wanted the true class to be actually the highest class score. Whereas for some of these other examples, like the car, for example, you see that the automobile class has a score of 6, which is much higher than any of the others, so that's good. And the frog, the predicted scores are maybe -4, which is much lower than all the other ones. So that's actually bad. So this is kind of a hand-wavy approach, just kind of looking at the scores and eyeballing which ones are good and which ones are bad. But to actually write algorithms about these things and to actually determine automatically which W will be best, we need some way to quantify the badness of any particular W. And that's this function that takes in a W, looks at the scores, and then tells us how bad quantitatively is that W, is something that we'll call a loss function. And in this lecture, we'll see a couple examples of different loss functions that you can use for this image classification problem. So then once we've got this idea of a loss function, this allows us to quantify for any given value of W, how good or bad is it. But then we actually need to come up with an efficient procedure for searching through the space of all possible W's and actually come up with what is the correct value of W that is the least bad. And this process will be an optimization procedure, and we'll talk more about that in this lecture. So I'm going to shrink this example a little bit because 10 classes is a little bit unwieldy. So we'll kind of work with this tiny toy data set of 3 examples and 3 classes going forward in this lecture. Again, in this example, like the cat is maybe not so correctly classified. The car is correctly classified. And the frog this setting of W got this frog image totally wrong because the frog score is much lower than the others. So to formalize this a little bit, usually when we talk about a loss function, we imagine that we have some training data set of x's and y's, usually n examples of these, where the x's are the inputs to the algorithm. In the image classification case, the x's would be the actually pixel values of your images. And the y's will be the things you want your algorithm to predict. We usually call these the labels or the targets. So in the case of image classification, remember, we're trying to categorize each image for CFAR 10 into one of 10 categories. So the label y here will be an integer between 1 and 10, or maybe between 0 and 9, depending on what programming language you're using. But it'll be an integer telling you what is the correct category for each one of those images x. And now our loss function will denote li to denote so then we have this prediction function x, which takes in our example x and our weight matrix w and makes some prediction for y. In the case of image classification, these will be our 10 numbers. Then we'll define some loss function li, which will take in the predicted scores coming out of the function f, together with the true target or label y, and give us some quantitative value for how bad those predictions are for that training example. And now the final loss L will be the average of these losses summed over the entire data set, over each of the n examples in our data set. So this is actually a very general formulation and actually extends even beyond image classification. Kind of as we move forward and see other examples of tasks in deep learning, the kind of generic setup is that for any task, you have some x's and y's, and you want to write down some loss function that quantifies exactly how happy you are with your particular parameter settings w, and then you'll eventually search over the space of w to find the w that minimizes the loss on your training data. So as a first example of a concrete loss function that is a nice thing to work with in image classification, we'll talk about the multi-class SVM loss. You may have seen the binary SVM or support vector machine in CS229. And the multi-class SVM is a generalization of that to handle multiple classes. In the binary SVM case, as you may have seen in 229, you only had 2 classes. Each example X was going to be classified as either a positive or negative example. But now we have 10 categories. So we need to generalize this notion to handle multiple classes. So this loss function has kind of a funny functional form. So we'll walk through it in quite a bit of detail over the next couple of slides. But what this is saying is that the loss Li for any individual example, the way we'll compute it is we're going to perform a sum over all of the categories y except for the true category yi. So we're going to sum over all the incorrect categories, and then we're going to compare the score of the correct category and the score of the incorrect category. And now, if the score for the correct category is greater than the score of the incorrect category, greater than the incorrect score by some safety margin that we set to 1, if that's the case, that means that the true score is the score for the true category is, if it's much larger than any of the false categories, then we'll get a loss of 0. And we'll sum this up over all of the incorrect categories for our image. And this will give us our final loss for this one example in the data set. And again, we'll take the average of this loss over the whole training data set. So this kind of like if-then statement, like if the true class score is much larger than the others, this kind of if-then formulation, we often compactify into this single max of 0 sj minus syij plus 1 thing. But I always find that notation a little bit confusing, and it always helps me to write it out in this sort of case-based notation to figure out exactly what the 2 cases are and what's going on. And by the way, this style of loss function, where we take max of 0 and some other quantity, is often referred to as some type of a hinge loss. And this name comes from the shape of the graph when you go and plot it. So here, the x-axis corresponds to the SYI. That is the score of the true class for some training example. And now the y-axis is the loss. And you can see that as the score for the true category for this example increases, then the loss will go down linearly until we get to above this safety margin, and after which the loss will be 0 because we've already correctly classified this example. So question? Yeah, so the question is, in terms of notation, what is S and what is SYI in particular? So the S's are the predicted scores for the classes that are coming out of the classifier. So like if 1 is the cat class and 2 is the dog class, then S1 and S2 would be the cat and dog scores respectively. And remember we said that YI was the category of the ground truth label for the example, which is some integer. So then S sub Y sub I, sorry for the double subscript, that corresponds to the score of the true class for the ith example in the training set. Question? Yeah, the question is, what exactly is this computing here? It's a little bit funny. I think it'll become more clear when we walk through an explicit example. But in some sense, what this loss is saying is that we are happy if the true score is much higher than all the other scores. It needs to be higher than all the other scores by some safety margin. And if the true score is not high enough, greater than any of the other scores, then we will incur some loss, and that will be bad. So this might make a little bit more sense if you walk through an explicit example for this tiny 3-example data set. So here, remember, I've sort of removed the case-based notation and just switching back to the 0, 1 notation. And now if we think about computing this multi-class SVM loss for just this first training example on the left, then remember, we're going to loop over all of the incorrect classes. So for this example, cat is the correct class. So we're going to loop over the car and frog classes. And now for car, we're going to look at the car score, 5.1, minus the cat score, 3.2, plus 1. When we're comparing cat and car, we expect to incur some loss here because the car score is greater than the cat score, which is bad. So for this one class, for this one example, we'll incur a loss of 2.9. And then when we go and compare the cat score and the frog score, we see that cat is 3.2, frog is minus 1.7. So cat is more than 1 greater than frog, which means that between these two classes, we incur 0 loss. So then the multi-class SVM loss for this training example will be the sum of the losses across each of these pairs of classes, which will be 2.9 plus 0, which is 2.9. Which is sort of saying that 2.9 is a quantitative measure of how much our classifier screwed up on this one training example. And then if we repeat this procedure for this next car image, then again, the true class is car. So we're going to iterate over all of the other categories. When we compare the car and the cat score, we see that car is more than 1 greater than cat, so we get no loss here. When we compare car and frog, we again see that the car score is more than 1 greater than frog, so we get, again, no loss here. And our total loss for this training example is 0. And now, I think you hopefully get the picture by now, but if you go look at frog, now frog, we again compare frog and cat, incur quite a lot of loss because the frog score is very low. Compare frog and car, incur a lot of loss because the score is very low. And then our loss for this example is 12.9. And then our final loss for the entire data set is the average of these losses across the different examples. So when you sum those out, it comes to about 5.3. So then it's this is our quantitative measure that our classifier is 5.3 bad on this data set. Was there a question? Yeah, the question is, how do you choose the +1? That's actually a really great question. It seems like kind of an arbitrary choice here. Like, it's the only constant that appears in the loss function, and that seems to offend your aesthetic sensibilities a bit, maybe. But it turns out that this is somewhat of an arbitrary choice. You can kind of because we don't actually care about the absolute values of the scores in this loss function. We only care about the relative differences between the scores. We only care that the correct score is much greater than the incorrect scores. So in fact, if you imagine scaling up your whole W up or down, then it kind of rescales all the scores correspondingly. And if you kind of work through the details, and there's a detailed derivation of this in the course notes online, you find that this choice of 1 actually doesn't matter. That this free parameter of 1 kind of washes out and is canceled with the scale, like the overall setting of the scale in W. And again, check the course notes for a bit more detail on that. So then I think it's kind of useful to think about a couple different questions to try to understand intuitively what this loss is doing. So the first question is, what's going to happen to the loss if we change the scores of the car image just a little bit? Any ideas? Everyone's too scared to ask a question? Answer? Yeah, so the answer is that if we jiggle the scores for this car image a little bit, the loss will not change. So the SVM loss, remember, the only thing it cares about is getting the correct score to be greater than 1 more than the incorrect scores. But in this case, the car score is already quite a bit larger than the others. So if the scores for this class for this example change just a little bit, this margin of 1 will still be retained, and the loss will not change. We'll still get 0 loss. The next question, what's the min and max possible loss for SVM? Well, I hear some murmurs. So the minimum loss is 0. Because if you can imagine that across all the classes, if our correct score was much larger, then we'll incur 0 loss across all the classes, and it'll be 0. And if you think back to this hinge loss plot that we had, then you can see that if the correct score goes very, very negative, then we could incur potentially infinite loss. So the min is 0 and the max is infinity. Another question, sort of when you initialize these things and start training from scratch, usually you kind of initialize W with some small random values. As a result, your scores tend to be sort of small, uniform random values at the beginning of training. And then the question is that if all of your S's, if all of the scores are approximately 0 and approximately equal, then what kind of loss do you expect when you're using the multi-class SVM? Yeah, so the answer is number of classes minus 1. Because remember that if we're looping over all of the incorrect classes, so we're looping over C minus 1 classes, within each of those classes, the two S's will be about the same. So we'll get a loss of 1 because of the margin, and we'll get C minus 1. So this is actually kind of useful because this is a useful debugging strategy when you're using these things, that when you start off training, you should think about what you expect your loss to be. And if the loss you actually see at the start of training at that first iteration is not equal to C minus 1 in this case, that means you probably have a bug and you should go check your code. So this is actually kind of a useful thing to be checking in practice. Another question, what happens if, so I said we're summing an SVM over the incorrect classes. What happens if this sum is also over the correct class, if we just go over everything? Yeah, so the answer is that the loss increases by 1. And I think the reason that we do this in practice is because normally loss of 0 is kind of has this nice interpretation that you're not losing at all, so that's nice. So I think your answers wouldn't really change. You would end up finding the same classifier if you actually looped over all the categories. But it's just by conventions, it omit the correct class so that our minimum loss is 0. So another question, what if we used mean instead of sum here? Yeah, the answer is that it doesn't change. So the number of classes is going to be fixed ahead of time when we select our data set. So that's just rescaling the whole loss function by a constant. So it doesn't really matter. It'll sort of wash out with all the other scale things because we don't actually care about the true values of the scores. Or the true value of the loss, for that matter. So now here's another example. What if we change this loss formulation and we actually added a square term on top of this max? Would this end up being the same problem, or would this be a different classification algorithm? Yes, this would be different. So here the idea is that we're kind of changing the trade-offs between good and badness in kind of a nonlinear way. So this would end up actually computing a different loss function. This idea of a squared hinge loss actually does get used sometimes in practice. So that's kind of another trick to have in your bag when you're making up your own loss functions for your own problems. So now you'll end up, oh, was there a question? Yeah, so the question is, why would you ever consider using a squared loss instead of a non-squared loss? And the whole point of a loss function is to kind of quantify how bad are different mistakes. And if the classifier is making different sorts of mistakes, how do we weigh off the different trade-offs between different types of mistakes the classifier might make? So if you're using a squared loss, that sort of says that things that are like very, very bad are now going to be squared bad. So that's like really, really bad. Like we don't want anything that's totally catastrophically misclassified. Whereas if you're using this hinge loss, then we don't actually care between being a little bit wrong and being a lot wrong. Kind of like if an example is a lot wrong and we increase it and make it a little bit less wrong, that's kind of the same goodness as an example which was only a little bit wrong and then increasing it to be a little bit more right. So that's a little bit hand-wavy, but this idea of using a linear versus a square is a way to quantify how much we care about different categories of errors. And this is definitely something that you should think about when you're actually applying these things in practice. Because the loss function is the way that you tell your algorithm what types of errors you care about and what types of errors it should trade off against. So that's actually super important in practice, depending on your application. So here's just a little snippet of sort of vectorized code in NumPy. And you'll end up implementing something like this for the first assignment. But this kind of gives you the sense that this sum is actually like pretty easy to implement in NumPy. It only takes a couple lines of vectorized code. And you can see in practice, like one nice trick is that we can actually go in here and zero out the margins corresponding to the correct class. And that makes it easy to then just that's sort of one nice vectorized trick to skip, like iterate over all but one class. You just kind of zero out the one that you want to skip and then compute the sum anyway. So that's a nice trick you might consider using on the assignment. So now, another kind of question about this loss function. Suppose that you were lucky enough to find a W that has loss of 0. Like, you're not losing at all. You're totally winning. This loss function is crushing it. But then there's a question. Is this W unique, or were there other Ws that could also have achieved 0 loss? Answer? Yeah, so there are definitely other Ws. And in particular, because we talked a little bit about this thing of scaling the whole problem up or down depending on W. So you could actually take W multiplied by 2, and this doubled W, is it a quad U then? I don't know. This would also achieve 0 loss. So as a kind of concrete example of this, you can go back to your favorite example and maybe work through the numbers a little bit later. But if you're taking W and we double W, then the margins between the correct and incorrect scores will also double. So that means that if all these margins were already greater than 1, and we doubled them, they're still going to be greater than 1, so you'll still have 0 loss. And this is kind of interesting, right? Because if our loss function is the way that we tell our classifier which W we want and which W we care about, this is a little bit weird. Now there's this inconsistency, and how is the classifier to choose between these different versions of W that all achieve 0 loss? And that's because what we've done here is written down only a loss in terms of the data, and we've only told our classifier that it should try to find a W that fits the training data. But really, in practice, we don't actually care that much about fitting the training data. The whole point of machine learning is that we use the training data to find some classifier, and then we'll apply that thing on test data. So we don't really care about the training data performance. We really care about the performance of this classifier on test data. So as a result, if the only thing we're telling our classifier to do is fit the training data, then we can kind of lead ourselves into some of these weird situations sometimes, where the classifier might have unintuitive behavior. So kind of a concrete canonical example of this sort of thing. By the way, this is not linear classification anymore. This is a little bit of a more general machine learning concept. Is that suppose we have this data set of blue points, and we're going to fit some curve to the training data, the blue points. Then if the only thing we've told our classifier to do is to try and fit the training data, it might go in and have very wiggly curves to try to perfectly classify all of the training data points. But this is bad because we don't actually care about this performance. We care about the performance on the test data. So now if we have some new data come in that sort of follows the same trend, then this very wiggly blue line is going to be totally wrong. And in fact, what we probably would have preferred the classifier to do was maybe predict this straight green line rather than this very complex wiggly line to perfectly fit all the training data. And this is kind of a full core fundamental problem in machine learning. And the way we usually solve it is this concept of regularization. So here, we're going to add an additional term to the loss function. In addition to the data loss, which will tell our classifier that it should fit the training data, we'll also typically add another term to the loss function called a regularization term, which encourages the model to somehow pick a simpler W, where the concept of simple kind of depends on the task and the model. But the whole idea is that there's this whole idea of Occam's razor, which is kind of this fundamental idea in scientific discovery more broadly, which is that if you have many different competing hypotheses that could explain your observations, you should generally prefer the simpler one, because that's the explanation that is more likely to generalize to new observations in the future. And the way that we operationalize this intuition in machine learning is typically through some explicit regularization penalty that's often written down as R. So then your standard loss function usually has these two terms, a data loss and a regularization loss. And there's some hyperparameter here, lambda, that trades off between the two. And we talked about hyperparameters and cross-validation in the last lecture. So this regularization hyperparameter lambda will be one of the more important ones that you'll need to tune when training these models in practice. Question? Yeah, so the question is, what's the connection between this lambda RW term and actually forcing this wiggly line to become a straight green line? So you can sort of, I didn't want to go through the derivation on this because I thought it would sort of lead us too far astray. But you can imagine maybe you're doing a regression problem in terms of different basis functions, like polynomial basis functions. And if you're adding this regression penalty, you can encourage the model. You can, like, maybe the model has access to polynomials of very high degree. But through this regression term, you could encourage the model to prefer polynomials of lower degree if they fit the data properly, or if they fit the data relatively well. So you could imagine there's sort of two ways to do this. Either you can constrain your model class to just not contain the more powerful, more complex models, or you can kind of add this soft penalty where the model still has access to more complex models, maybe high-degree polynomials in this case, but you add this soft constraint saying that if you want to use these more complex models, you need to overcome this penalty for using their complexity. So that's kind of the connection here. That is not quite linear classification, but this is the kind of picture that many people have in mind when they think about regularization, at least. So there's actually a lot of different types of regularization that get used in practice. The most common one is probably L2 regularization or weight decay, but there's a lot of other ones that you might see. So this L2 regularization is just the Euclidean norm of this weight vector W, or sometimes the squared norm, or sometimes half the squared norm because it makes your derivatives work out a little bit nicer. But the idea of L2 regularization is you're just penalizing the Euclidean norm of this weight vector. You might also sometimes see L1 regularization, where we're penalizing the L1 norm of the weight vector. And the L1 regularization has some nice properties like encouraging sparsity in this matrix W. Some other things you might see would be this elastic net regularization, which is some combination of L1 and L2. You sometimes see max norm regularization, which like penalizing the max norm rather than the L1 or L2 norm. And but these sorts of regularizations are things that you kind of see not just in deep learning, but across many areas of machine learning and even optimization more broadly. But in this class, in some later lectures, we'll also see some types of regularization that are more specific to deep learning. For example, dropout we'll see in a couple lectures, or batch normalization, stochastic depth. These things get kind of crazy in recent years. But the whole idea of regularization is just anything that you do to your model that sort of penalizes somehow the complexity of the model rather than explicitly trying to fit the training data. Question? Yeah, so the question is, how does the L2 regularization measure the complexity of the model? Thankfully, we have an example of that right here. Maybe we can walk through. So here, we maybe have some training example X, and there's two different W's that we're considering. So X is just this vector of 4 ones, and we're considering these two different possibilities for W. One is a 1 in the first, one has a single 1 and 3 zeros, and the other has this 0.25 spread across the 4 different entries. And now, when we're doing linear classification, we're really taking dot products between our X and our W. So in terms of like linear classification, these two W's are the same because they give the same result when dot producted with X. But now the question is, if you look at these two examples, then which one would L2 regression prefer? Yeah, so L2 regression would prefer W2 because it has a smaller norm. So the answer is that the L2 regression kind of measures complexity of the classifier in this kind of relatively coarse way, where the idea is that, remember the W's in linear classification had this interpretation of how much does this value of the vector X correspond to this output class. So L2 regularization is saying that it kind of prefers to spread that influence across all the different values in X. Maybe this might be more robust in case you come up with X's that sort of vary, then our decisions are kind of spread out and depend on the entire X vector, rather than depending only on certain elements of the X vector. And by the way, L1 regularization kind of has this opposite interpretation. So actually, if we were using L1 regularization, then we would actually prefer W1 over W2, because L1 regularization has this different notion of complexity, saying that maybe the model is less complex if it only has, maybe we measure model complexity by the number of zeros in the weight vector. So the question of how do we measure complexity and how does L2 measure complexity, they're kind of problem dependent, and you kind of have to think about, for your particular setup, for your particular model and data, how do you think that complexity should be measured on this task? Question? Oh, yes, you're right. So in this case, L1 is actually the same between these two. But maybe if we set the W, you could construct a similar example to this where W1 would be preferred by L1 regularization. I guess the general intuition behind L1 is that it generally prefers sparse solutions, that it kind of drives all your entries of W to 0 for most of the entries, except for a couple where it's allowed to deviate from 0. So kind of the way of measuring complexity for L1 is maybe the number of non-zero entries. And then for L2, it thinks that things that spread the W across all the values are less complex. So it kind of depends on your data, depends on your problem. Oh, and by the way, if you're a hardcore Bayesian, then using L2 regularization has kind of this nice interpretation of map inference under a Gaussian prior on the parameter vector. I think there was a homework problem about that in 229, but we won't talk about that for the rest of the quarter. Okay, so if that's sort of like my sort of long deep dive into the multi-class SVM loss. Question? Yeah, so the question is that this is still not like adding regularization is not going to change the hypothesis class. This is not going to change us away from a linear classifier. So the idea is that maybe this example of this polynomial regression is definitely not linear regression. That could be seen as linear regression on top of like a polynomial expansion of the input, and in which case then this regression sort of says that you're not allowed to use as many polynomial coefficients as maybe you should have, right? So you can imagine this as like when you're doing polynomial regression, like you can write out a polynomial as like f of x equals like a0 plus a1x plus a2x squared plus a3x, whatever. In that case, your parameters, your w's, would be these a's, in which case this double, like penalizing the w could force it towards lower degree polynomials. Except in the case of polynomial regression, you don't actually want to parameterize in terms of a's. There's some other parameterization that you want to use. But that's kind of the general idea, that you're sort of penalizing the parameters of the model to force it towards the simpler hypotheses within your hypothesis class. And maybe we can take this offline if that's still a bit confusing. OK, so then we've sort of seen this multi-class SVM loss. And just by the way, as a side note, this is sort of one extension or generalization of the SVM loss to multiple classes. There's actually a couple different formulations that you can see around in the literature. But I mean, kind of my intuition is that they all tend to work kind of similarly in practice, at least in the context of deep learning. So we'll kind of stick with this one particular formulation of the multi-class SVM loss in this class. But of course, there's many different loss functions you might imagine. So another really popular choice, in addition to the multi-class SVM loss, another really popular choice in deep learning is this multinomial logistic regression, or a softmax loss. And this one is probably actually a bit more common in the context of deep learning, but I decided to present it second for some reason. So remember, in the context of the multi-class SVM loss, we didn't actually have an interpretation for those scores. Remember, when we're doing some classification, our model F spits out these 10 numbers, which are our scores for the classes. And for the multi-class SVM, we didn't actually give much interpretation to those scores. We just said that we want the true score, the score of the correct class, to be greater than the incorrect classes. And beyond that, we don't really say what those scores mean. But now for the multinomial logistic regression loss function, we actually will endow those scores with some additional meaning. And in particular, we're going to use those scores to compute a probability distribution over our classes. So we use this so-called softmax function, where we take all of our scores, we exponentiate them so that now they become positive, then we renormalize them by the sum of those exponents. So now after we go through this, after we send our scores through this softmax function, now we end up with this probability distribution, where now we have probabilities over our classes where each probability is between 0 and 1, and the sum of probabilities across all classes sum to 1. And now kind of the interpretation is that we kind of want to, there's this computed probability distribution that's implied by our scores, and we want to compare this with the target or true probability distribution. So if we know that the thing is a cat, then the target probability distribution would put all of the probability mass on cat. So we would have probability of cat equals 1 and 0 probability for all the other classes. So now what we want to do is encourage our computed probability distribution that's coming out of this softmax function to match this target probability distribution that has all the mass on the correct class. And the way that we do this, I mean, you can view this equation in many ways. You can view this as a KL divergence between the target and the computed probability distribution. You can view this as a maximum likelihood estimate. But at the end of the day, what we really want is that the probability of the true class is high and is close to 1. So then our loss will now be the negative log of the probability of the true class. This is kind of confusing because we're kind of putting this through multiple different things. But remember, we wanted the probability to be close to 1. So now log is a monotonic function that kind of goes like this. And it turns out mathematically it's easier to maximize log than it is to maximize the raw probability. So we stick with log. And now log is monotonic. So if we maximize log p of correct class, that means we want that to be high. But loss functions measure badness, not goodness. So we need to put in the -1 to make it go the right way. So now our loss function for SVM is going to be the minus log of the probability of the true class. Yeah, so that's kind of the summary here, is that we take our scores, we run through the softmax, and now our loss is this minus log of the probability of the true class. Okay, so then if you kind of look at what this looks like on a concrete example, then we go back to our favorite cat, our favorite beautiful cat with our 3 examples, and we've got these 3 scores that are coming out of our linear classifier, and these scores are exactly the way that they were in the context of the SVM loss. But now, rather than taking these scores and putting them directly into our loss function, we're going to take them all and exponentiate them so that they're all positive, and then we'll normalize them to make sure that they all sum to 1. And now our loss will be the minus log of the true class score. So that's kind of the softmax loss, or also called multinomial logistic regression. So now we asked several questions to try to gain intuition about the multi-class SVM loss. And it's kind of useful to think about some of the same questions to contrast with the softmax loss. So then the question is, what's the min and max value of the softmax loss? Okay, maybe not so sure. There's too many logs and sums and stuff going on in here. But remember, so the answer is that the min loss is 0 and the max loss is infinity. And the way that you can see this is that if the probability distribution that we want is 1 on the correct class, 0 on the incorrect classes, the way that we do that, so if that were the case, then this e to this term would end up, this thing inside the log would end up being 1, because it's the probability, well, log probability of the true class. Then log of 1 is 0, minus log of 0 is, or minus log of 1 is still 0. So that means that if we got the thing totally right, then our loss would be 0. But by the way, in order to get the thing totally right, what would our scores have to look like? Murmuring. So the scores would actually have to go quite extreme, like towards infinity. So because we actually have this exponentiation, this normalization, the only way we can actually get a probability distribution of 1 and 0 is actually putting an infinite score for the correct class and minus infinity score for all the incorrect classes. And computers don't do so well with infinities. So in practice, you'll never get to 0 loss on this thing with finite precision. But you still have this interpretation that 0 is the theoretical minimum loss here. And the maximum loss is unbounded. So suppose that if we had 0 probability mass on the correct class, then you would have minus log of 0. Log of 0 is like minus infinity. So minus log of 0 would be plus infinity. So that's really bad. But again, you'll never really get here, because the only way you can actually get this probability to be 0 is if e to the correct class score is 0, and that can only happen if that correct class score is minus infinity. So again, you'll never actually get to these minimum and maximum values with finite precision. So then, remember we had this sort of debugging sanity check question in the context of the multi-class SVM, and we can ask the same for the softmax. If all the s's are small and about 0, then what is the loss here? Yeah, answer? So minus log of 1 over c. I think that's, yeah. So then it would be minus log of 1 over c, which is, because log, you can flip the things, then it's just log of c. Yeah, so it's just log of c. And again, this is kind of a nice debugging thing. If you're training a model with this softmax loss, you should check at the first iteration. If it's not log c, then something's gone wrong. So then we can kind of compare and contrast these two loss functions a bit. That in terms of linear classification, the setup looks the same. We've got this W matrix that gets multiplied against our input to produce this vector of scores. And now the difference between the two loss functions is how we choose to interpret those scores to quantitatively measure the badness afterwards. So for SVM, we were going to go in and look at the margins between the true and the scores of the correct class and the scores of the incorrect class. Whereas for this softmax or cross-entropy loss, we're going to go and compute a probability distribution and then look at the minus log probability of the correct class. So sometimes if you look at like in the terms of, never mind, I'll skip that point. So another question that's kind of interesting when contrasting these two loss functions is thinking, suppose that I've got this example point, and if you change its scores, so assume that we've got 3 scores for this. Ignore the part on the bottom. But what happens, remember if we go back to this example where in the multi-class SVM loss, when we had the car, and the car was much better than all the other the car score was much better than all the incorrect classes, then jiggling the scores for that car image didn't change the multi-class SVM loss at all. Because the only thing that the SVM loss cared about was getting that correct score to be greater than a margin above the incorrect scores. But now the softmax loss is actually quite different in this respect. The softmax loss actually always wants to drive that probability mass all the way to 1. So even if you're giving very high score to the correct class and very low score to all the incorrect classes, softmax will want you to pile more and more probability mass on the correct class and continue to push the score of that correct class up towards infinity, and the score of the incorrect classes down towards minus infinity. So that's kind of an interesting difference between these two loss functions in practice. That SVM kind of, it'll get this data point kind of over the bar to be correctly classified, and then just give up. It doesn't care about that data point anymore. Whereas softmax will just always try to continually improve every single data point to get better and better and better and better. So that's kind of an interesting difference between these two functions. In practice, I think it tends not to make a huge difference which one you choose. They tend to perform pretty similarly across at least a lot of deep learning applications. But it is very useful to keep some of these differences in mind. Yeah, so to kind of recap where we've come to from here is that we've got some data set of x's and y's. We use our linear classifier to get some score function to compute our scores s from our inputs x. And then we'll use a loss function, maybe softmax or SVM or some other loss function, to compute how quantitatively bad were our predictions compared to this ground truth targets y. And then we'll often augment this loss function with a regularization term that tries to trade off between fitting the training data and preferring simpler models. So this is kind of a pretty generic overview of a lot of what we call supervised learning. And what we'll see in deep learning as we sort of move forward is that generally you'll want to specify some function f that could be very complex in structure, specify some loss function that determines how well your algorithm is doing given any value of the parameters, some regularization term for how to penalize model complexity, and then you combine these things together and try to find the w that minimizes this final loss function. But then the question is, how do we actually go about doing that? How do we actually find this w that minimizes the loss? And that leads us to the topic of optimization. So when we're doing optimization, I usually think of things in terms of like walking around some large valley. So the idea is that you're walking around this like large valley with different mountains and valleys and streams and stuff, and every point on this landscape corresponds to some setting of the parameters w. And you're this little guy who's walking around this valley, and you're trying to find, and the height of each of these points, is equal to the loss incurred by that setting of w. And now your job is, as this little man walking around this landscape, you need to somehow find the bottom of this valley. And this is kind of a hard problem in general. You might think like, maybe I'm really smart and I can think really hard about the analytic properties of my loss function, my regularization, all that. Maybe I can just write down the minimizer. And that would sort of correspond to magically teleporting all the way to the bottom of this valley. But in practice, once your prediction function f and your loss function and your regularizer, once these things get big and complex and using neural networks, then you can't really hope, there's really not much hope in trying to write down an explicit analytic solution that takes you directly to the minima. So in practice, we tend to use various types of iterative methods, where we start with some solution and then gradually improve it over time. So kind of the very first sort of stupidest thing that you might imagine is random search. That will just take a bunch of w's sampled randomly and throw them into our loss function and see how well they do. So spoiler alert, like this is a really bad algorithm. You probably shouldn't use this. But at least it's kind of one thing you might imagine trying. And we can actually do this. We can actually try to train a linear classifier via random search for CFAR10. And for this, there's 10 classes, so random chance is 10%. And if we did some number of random trials, we eventually found, just through sheer dumb luck, some setting of w that got maybe 15% accuracy. So that's better than random, but state of the art is maybe 95%. So we've got a little bit of gap to close here. So again, like probably don't use this in practice, but you might imagine that this is something you could potentially do. So in practice, maybe a better strategy is actually using some of the local geometry of this landscape. So if you're this little guy who's walking around this landscape, maybe you can't see like directly the path down to the bottom of the valley, but what you can do is kind of feel with your foot and figure out what is the local geometry, like which way, if I'm standing right here, which way will take me a little bit downhill. So then you can kind of feel with your feet and feel where is the slope of the ground taking me down a little bit in this direction. And you can take a step in that direction. And then you'll go down a little bit, feel again with your feet to figure out which way is down, and then repeat over and over again and kind of hope that you'll end up at the bottom of the valley eventually. So this also seems like a relatively simple algorithm, but actually this one tends to work really well in practice if you kind of get all the details right. So this is generally the strategy that we'll follow when training these large neural networks and linear classifiers and other things. So then, like that was a little hand-wavy. So what is slope? If you remember back to your calculus class, then at least in one dimension, the slope is equal to the derivative of this function. So if we've got some one-dimensional function f that takes in a scalar x and then outputs the height of some curve, then we can compute the slope or derivative at any point by imagining, like, if we take a small step h in any direction, and then compare, like, what is the slope of that, take a small step h and compare the difference in the function value over that step, and then drive the step size to 0, that will give us the slope of that function at that point. And this generalizes quite naturally to multivariable functions as well. So in practice, our x is maybe not a scalar, but a whole vector of, because remember, x is something like right? So x might be a whole vector. So we need to generalize this notion to multivariable things. And the generalization that we use of the derivative in the multivariable setting is the gradient. So the gradient is a vector of partial derivatives. So the gradient will have the same shape as x, and each element of the gradient will tell us what is the slope of the function f if we move in that coordinate direction. And the gradient turns out to have these very nice properties, which is that so the gradient is now a vector of partial derivatives, but it points in the direction of greatest increase of the function. And correspondingly, if you look at the negative gradient direction, that gives you the direction of greatest decrease of the function. And more generally, if you want to know what is the slope of my landscape in any direction, then that's equal to the dot product of the gradient with a unit vector describing that direction. So this gradient is super important because it gives you this sort of linear first-order approximation to your function at your current point. So in practice, a lot of deep learning is about computing gradients of your functions and then using those gradients to iteratively update your parameter vector. So one kind of naive way that you might imagine actually evaluating this gradient on a computer is using the method of finite differences, kind of going back to the limit definition of the gradient. So here on the left, we imagine that our current w is this parameter vector that maybe gives us some current loss of maybe 1.25. And our goal is to compute the gradient dw, which will be a vector of the same shape as w. And each slot in that gradient will tell us how much will the loss change if we move a tiny infinitesimal amount in that coordinate direction. So one thing you might imagine is just computing this via finite differences. That we have our w. We might try to increment the first element of w by a small value h, and then recompute the loss using our loss function and our classifier and all that. And maybe in this setting, if we move a little bit in the first dimension, then our loss will decrease a little bit from 1.2534 to 1.25322. And then we can use this limit definition to come up with this finite differences approximation to the gradient in this first dimension. And now you can imagine repeating this procedure in the second dimension, where now we take the first dimension, set it back to the original value, and now increment the second direction by a small step, and again, recompute the loss, and use this finite differences approximation to compute an approximation to the gradient in the second slot. And now repeat this again for the third, and on and on and on. So this is actually a terrible idea because it's super slow. So you might imagine that computing this function f might actually be super slow if it's like a large convolutional neural network. And this parameter vector w probably will not have 10 entries like it does here. It might have like tens of millions or even hundreds of millions for some of these large, complex deep learning models. So in practice, you'll never want to compute your gradients via finite differences because you'd have to wait for like hundreds of millions potentially of function evaluations to get a single gradient. And that would be super slow and super bad. But thankfully, we don't have to do that. Hopefully, you took a calculus course at some point in your lives. So you know that thanks to these guys, we can just write down the expression for our loss and then use the magical hammer of calculus to just write down an expression for what this gradient should be. And this will be way more efficient than trying to compute it analytically via finite differences. One, it'll be exact. And two, it'll be much faster since we just need to compute this single expression. So what this would look like is now if we go back to this picture of our current w, rather than sort of iterating over all the dimensions of w, we'll figure out ahead of time what is the analytic expression for the gradient, and then just write it down and go directly from the w and sort of compute the dw, or the gradient, in one step. And that will be much better in practice. So in summary, like this numerical gradient is something that's simple and kind of makes sense, but you won't really use it in practice. In practice, you'll always take an analytic gradient and use that when actually performing these gradient computations. However, one interesting note is that these numeric gradients are actually a very useful debugging tool. So say you've written some code and you wrote some code that computes the loss and the gradient of the loss, then how do you debug this thing? And how do you make sure that this analytic expression that you derived and wrote down in code is actually correct? So a really common debugging strategy for these things is to use the numeric gradient as sort of a unit test to make sure that your analytic gradient was correct. Again, because this is super slow and inexact, then when doing this numeric gradient checking, as it's called, you'll tend to scale down the parameter of the problem so that it actually runs in a reasonable amount of time. But this ends up being a super useful debugging strategy when you're writing your own gradient computations. So this is actually very commonly used in practice, and you'll do this on your assignments as well. So then once we know how to compute the gradient, then it leads us to this super simple algorithm that's like 3 lines, but turns out to be at the heart of how we train even these very biggest, most complex deep learning algorithms. And that's gradient descent. So gradient descent is like, first we initialize our w as some random thing. Then while true, we'll compute our loss and our gradient, and then we'll update our weights in the opposite of the gradient direction. Because remember that the gradient was pointing in the direction of greatest increase of the function, so minus gradient points in the direction of greatest decrease. So we'll take a small step in the direction of minus gradient, and just repeat this forever, and eventually your network will converge, and you'll be very happy, hopefully. But this step size is actually a hyperparameter. And this tells us that every time we compute the gradient, how far do we step in that direction? And this step size, also sometimes called a learning rate, is probably one of the single most important hyperparameters that you need to set when you're actually training these things in practice. Actually, for me, when I'm training these things, trying to figure out this step size or this learning rate is the first hyperparameter that I always check. Things like model size or regularization strength, I kind of leave until a little bit later. And getting the learning rate or step size correct is the first thing that I try to set at the beginning. So kind of pictorially, what this looks like is that maybe we've got this. Here's a kind of simple example in 2 dimensions. So here we've got maybe this bowl, that's showing our loss function, where where this like red region in the center is this region of low loss that we want to get to, and these blue and green regions towards the edge are higher loss that we want to avoid. So now we're going to start off our W at some random point in the space, and then we'll compute the negative gradient direction, which will sort of hopefully point us in the direction of the minima eventually. And if we repeat this over and over again, we'll hopefully eventually get to the exact minima. And what this kind of looks like in practice is, oh man, we've got this mouse problem again. So what this looks like in practice is that if we repeat this thing over and over again, then we will start off at some point, and then eventually just taking tiny gradient steps each time, you'll see that the parameter will arc in towards the center of this region of minima. And that's really what you want, because you want to get to low loss. And by the way, as a bit of a teaser, we saw on the previous slide this example of like very simple gradient descent, where at every step, we're just stepping in the direction of the gradient. But in practice, over the next couple lectures, we'll see that there are slightly fancier what are they called, these update rules, where you can take slightly fancier things to incorporate gradients across multiple time steps and stuff like that tend to work a little bit better in practice and are used much more commonly than this vanilla gradient descent when training these things in practice. And then, as a bit of a preview, we can look at some of these slightly fancier methods on optimizing this same problem. So again, the black will be this same gradient computation, and these green, I forgot which color they are, but these 2 other curves are using slightly fancier update rules to decide exactly how to use the gradient information to make our next step. So one of these is gradient descent with momentum. The other is this atom optimizer, and we'll see more details about those later in the course. But the idea is that we have this very basic algorithm called gradient descent, where we use the gradient at every time step to determine where to step next. And there exist different update rules which tell us how exactly do we use that gradient information. But it's all kind of the same basic algorithm of trying to go downhill at every time step. But there's actually one more little wrinkle that we should talk about. So remember that we defined our loss function as this, we defined a loss that computes how bad is our classifier doing at any single training example. And then we said that our full loss over the data set was going to be the average loss across the entire training set. But in practice, this n could be very, very large. Like if we're using the ImageNet data set, for example, that we talked about in the first lecture, then n could be like 1.3 million. So actually computing this loss could be actually very expensive and require computing perhaps millions of evaluations of this function. So that could be really slow. And actually, because the gradient is a linear operator, when you actually try to compute the gradient of this expression, you see that the gradient of our loss is now the sum of the gradient of the losses for each of the individual terms. So now if we want to compute the gradient, again, it sort of requires us to iterate over the entire training data set, all n of these examples. So if our n was like 1 million, this would be super, super slow. And we would have to wait a very, very long time before we make any individual update to W. So in practice, we tend to use what is called stochastic gradient descent, where rather than computing the loss and gradient over the entire training set, instead, at every iteration, we sample some small set of training examples called a mini batch. Typically, usually this is a power of 2 by convention, like 32, 64, 128 are kind of common numbers. And then we'll use this small mini batch to compute an estimate of the full sum and an estimate of the true gradient. And now this is stochastic because you can view this as maybe a Monte Carlo estimate of some expectation of the true value. So now this makes our algorithm slightly fancier, but it's still only 4 lines. So now it's while true, sample some random mini batch of data, now evaluate your loss and gradient on the mini batch, and now make an update on your parameters based on this estimate of the loss, and this estimate of the gradient. And again, we'll see slightly fancier update rules of exactly how to sort of integrate multiple gradients over time. But this is kind of the basic training algorithm that we use for pretty much all deep neural networks in practice. So we have another interactive web demo about how actually playing around with linear classifiers and training these things via stochastic gradient descent. But given how miserable the web demo was last time, I'm not actually going to open the link. Instead, I'll just play this video. So here, but I encourage you to go check this out and play with it online, because it actually helps to build some intuition about linear classifiers and training them via gradient descent. So here you can see on the left, we've got this problem where we're categorizing 3 different classes, and we've drawn the decision, and we've got these green, blue, and red points that are our training samples from these 3 classes. And now we've drawn the decision boundaries for these classes, which are the colored background regions, as well as these directions giving you the direction of increase for the class scores for each of these 3 classes. And now if you see, if you actually go and play with this thing online, you can see that we can go in and adjust the W's, and changing the values of the W's will cause these decision boundaries to rotate. If you change the biases, then the decision boundaries will not rotate, but will instead move side to side or up and down. Then we can actually make steps that are trying to update this loss. You can change the step size with this slider. You can hit this button to actually run the thing. So now with a big step size, we're running gradient descent right now, and these decision boundaries are flipping around and trying to fit the data. So it's kind of doing OK now. But then we can actually change the loss function in real time between these different SVM formulations and the different softmax. And you can see that as you flip between these different formulations of loss functions, it's kind of generally doing the same thing. Our decision regions are mostly in the same place, but exactly how they end up relative to each other and exactly what the trade-offs are between categorizing these different things changes a little bit. So I'd really encourage you to go online and play with this thing to try to get some intuition for what it actually looks like to try to train these linear classifiers via gradient descent. So now, as an aside, I'd like to sort of talk about another idea, which is that of image features. So far we've talked about linear classifiers, which is just maybe taking our raw image pixels and then feeding the raw pixels themselves into our linear classifier. But as we kind of talked about in the last lecture, this is maybe not such a great thing to do because of things like multimodality and whatnot. So in practice, actually feeding raw pixel values into linear classifiers tends to not work so well. So it was actually kind of common before the dominance of deep neural networks was instead to have this 2-stage approach, where first you would take your image and then compute various feature representations of that image that are maybe computing different kinds of quantities relating to the appearance of the image, and then concatenate these different feature vectors to give you some feature representation of the image. And now this feature representation of the image would be fed into a linear classifier, rather than feeding the raw pixels themselves into the classifier. And kind of the motivation here is that there might be, so imagine we have a training data set on the left of these red points, and red points in the middle, and blue points around that. And for this kind of data set, there's no way that we can draw a linear decision boundary to separate the red points from the blue points. And we kind of saw more examples of this in the last lecture. But if we use a clever feature transform, in this case transforming to polar coordinates, then now after we do the feature transform, then this kind of complex data set actually might become linearly separable and actually could be classified correctly by a linear classifier. And the whole trick here now is to kind of figure out what is the right feature transform that is sort of computing the right quantities for the problem that you care about. So like for images, maybe converting your pixels to polar coordinates doesn't make sense, but you actually can try to write down feature representations of images that might make sense and actually might help you out and might do better than putting in raw pixels into the classifier. So one example of this type of feature representation that's super simple is this idea of a color histogram. So you'll take maybe each pixel, you'll take this like hue color spectrum and divide it into buckets, and then for every pixel, you'll map it into one of those color buckets and then count up how many pixels fall into each of these different buckets. So this kind of tells you globally what kinds of colors are in the image. So maybe for this example of a frog, this feature vector would tell us that there's kind of a lot of green stuff and maybe not a lot of purple or red stuff. And this is kind of a simple feature vector that you might see in practice. Another kind of common feature vector that we saw before the rise of neural networks, or before the dominance of neural networks, was this histogram of oriented gradients. So remember from the first lecture that Hubel and Wiesel found that these oriented edges are really important in the human visual system. And this histogram of oriented gradients feature representation kind of tries to capture the same intuition and measure the local orientation of edges on the image. So what this thing is going to do is take our image and then divide it into these little 8 by 8 pixel regions. And then within each of those 8 by 8 pixel regions, we'll compute what is the dominant edge direction at each pixel, quantize those edge directions into several buckets, and then within each of those regions, compute a histogram over these different edge orientations. And now your full feature vector will be these different bucketed histograms of edge orientations across all the different 8 by 8 regions in the image. So this kind of gives you some, so this is in some sense dual to the color histogram classifier that we saw before. So color histogram is kind of saying globally what colors exist in the image. And this is kind of saying overall what types of edge information exists in the image. And even localized like to different parts of the image, what types of edges exist in different regions. So maybe for this frog on the left, you can see he's sitting on a leaf. And these leaves have these dominant diagonal edges. And if you kind of visualize the histogram of oriented gradient features, then you can see that in this region, we've got kind of a lot of diagonal edges that this histogram of oriented gradient feature representation is capturing. So this was a super common feature representation and was used a lot for object recognition, actually not too long ago. Another feature representation that you might see kind of out there is this idea of bag of words. So here we've got this is kind of taking inspiration from natural language processing. So if you've got like a paragraph, then kind of a way that you might represent a paragraph by a feature vector is kind of counting up the occurrences of different words in that paragraph. So we want to kind of take that intuition and apply it to images in some way. But the problem is that there's no like really simple, straightforward analogy of words to images. So we need to define our own vocabulary of visual words. And now, so then we take this kind of two-stage approach, where first we'll get a bunch of images, sample a whole bunch of tiny random crops from those images, and then cluster them using something like k-means to come up with these like different cluster centers that are representing maybe different types of visual words in the images. So if you look at this example on the right here, this is kind of a real example of clustering actually different image patches from images. And you can see that after this clustering step, our visual words capture like these different colors, like red and blue and yellow, as well as these different types of oriented edges in different directions, which is kind of interesting that now we're starting to see these oriented edges kind of come out from the data in a data-driven way. And now once we've got these set of visual words, also called a codebook, then we can encode our image by trying to say, for each of these visual words, how much does this visual word occur in the image? And now this gives us, again, some slightly different information about what is the visual appearance of this image. And this was actually this is a type of feature representation that Feifei worked on when she was a grad student. So it's actually, so this is something that you saw in practice not too long ago. So then kind of as a bit of a teaser, kind of tying this all back together, kind of the way that this image classification pipeline might have looked like maybe about 5 to 10 years ago would be that you would take your image and then compute these different feature representations of your image, things like bag of words or histogram of oriented gradients, concatenate a whole bunch of features together, and then feed these feature extractors down into some linear classifier. I'm simplifying a little bit. The pipelines were a little bit more complex than that, but this is kind of the general intuition. And then the idea here was that after you extracted these features, this feature extractor would be kind of a fixed block that would not be updated during training. And during training, you would only update the linear classifier that's working on top of features. And actually, I would argue that once we move to convolutional neural networks and these deep neural networks, it actually doesn't look that different. The only difference is that rather than sort of writing down the features ahead of time, we're going to learn the features directly from the data. So we'll take our raw pixels and feed them into this convolutional network, which will end up computing through many different layers some type of feature representation driven by the data. And then we'll actually train this entire weights for this entire network rather than just the weights of the linear classifier on top. So next time, we'll really start diving into this idea in more detail, and we'll introduce some neural networks and start talking about backpropagation as well.